So this is the little mini unit here on chapter 8, winter unit here, and it's on measurement, chapter 8 from the textbook. And we start off with the Pythagorean theorem. So Pythagorean theorem, a lot of you should know this. It's a squared plus b squared equals c squared. It works for right angled triangles. The reason it works is if you go ahead and you square this side and give it an area, and square this side and give it an area, it will be the same size as this guy here squared. So if you don't believe me, you can have a basic Pythagorean triple, 3, 4, and 5, and that works because 3 squared plus, let me do it down here, 3 squared plus 4 squared equals 5 squared. That's 9 and 16 equals 25, 25 equals 25. What you notice is here, if you made a square that was 4 by 4, you'd have 16 little squares. Here you'd have 3 by 3, 9 little squares. And then here you'd have, because this is 5 by 5, you'd have 25 little squares. So you could take this 16 and put it on here. 16 less, 25 less 16 will leave you 9, and then you got these squares here. Okay, anyway, it works for any right angled triangle. A squared plus b squared equals c squared. So when you look at this and you're looking for the hypotenuse, I don't think I mentioned that, the long side opposite of the right angle is called the hypotenuse. And to solve it, you put c squared equals a squared plus b squared. You square this side, square that side, or vice versa, add them together, and then take the square root to get what is the hypotenuse. If you're looking for a side that is not the hypotenuse, like in this case here, you can either set it up so you have c squared equals a squared plus b squared still, or write it the other way around, a squared plus b squared equals c squared. And then sub in, so you would have here 4.5 squared equals 2 squared plus b squared, and then solve for b squared. Or you can use a different equation. So when you're looking for not the right angle, what you can do, or sorry, not the hypotenuse, what you do is you set it up so that it's the side that you're missing squared equals the hypotenuse squared, subtract the other side squared. So b squared equals c squared minus a squared, or if you're looking for a squared, it'd be c squared minus b squared. Okay, so the difference between this and the regular formula is that you subtract when you're looking for one of the smaller sides, you add when you're looking for a hypotenuse. This question here I thought was pretty good. Here you have two sides and they're both the same length, and you still use c squared equals a squared plus b squared to figure these guys out. But what you notice is that since this is the same length and we don't have either of these, you might think we can't do this, but what happens here is since a is equal to b, you can sub b equals a into the equation and then get c squared equals a squared plus a squared. Okay, because now I've replaced b with a, and I have a squared plus a squared, which is 2a squared when you collect like terms. C squared equals 2a squared. Then when you put the 3.6 in for c, and square it, you'll get 1296. 1296 is equal to 2a squared divided by 2, and then get the square root. So that's a tough one, okay? But the other ones I think you should do. This does carry forward to grade 10, so make sure you know how to do this. I'm sure you've seen this year after year. So that's Pythagorean theorem. The reason we do it is it helps with composite figures. So when we go to get the areas of composite figures, now make sure that you remember that you have access to that formula sheet. It's the EQAO formula sheet for all shapes. We will have access to that for the whole year. So whenever you need something for formula, you don't have to memorize them. But when we do use those formulas to help get the areas and perimeters of composite figures. So a composite figure is just a shape that we know, like a square, added to like half a circle, or maybe you throw a half a triangle in, or a whole triangle in here, or whatever. And we put these pieces together and we try to figure out the areas. So you obey the same rules as before. Perimeter here, if you're going on the perimeter, you want to go around this shape. So you know this is 2, you know this is 3, you know that top guy is 3, you know this is 2. What's missing here is this side, which is called x. And we don't know x, but we do know this side and this side of the triangle. So we use Pythagorean theorem down here to figure out that this is 2.8 centimeters squared. So you can pause this now if you want to go over how I did this. I got x squared equals 2 squared plus 2 squared, this squared and this squared, 4 root x is 8, x squared is 8, x is the root of 8, which is 2.8. So now this is 2.8. And then to get the perimeter of this composite shape, you just add all the sides up. To get the area of the composite shape, you break this up into two pieces. You got your rectangle here. So you have the area of the rectangle, which is length times width. And then you have the area of this triangle, which I'm making this picture a little ugly. And the area of the triangle is 1/2 base height. Again, you get that off the formula sheet if you don't remember it, okay? So length times width, real easy, 2 times 3. That'll get you 6. And then base and height, in this case, it was this guy here times this guy here. That's your base. And that was 2. If this height over here is 2, then this height over here is 2. So you can call that the H. This is the B. That's also 2. 1/2, 2 times 2 is 2. Add them together to get 8. And remember that area units are squared. Okay, so 8 centimeters squared. This guy here going around, what's the issues that we need? We have a couple unknown y and x. Probably going to need them to find out what they are anyway. So why don't we just figure them out. X is going to be, this is 27, this is 13, so add them together to get 40. So this is 40. And y, if that's 47 and that's 25, subtract those two to get 22. Okay, so now we got all the pieces we need for the perimeter. Just go all the way around. And then to get the area, you break it up into two rectangles that you can figure out. You could probably go this way too. You could probably cut it this way if you felt like it. I cut it this way. You get the same answer either way. If you cut it this way, I call this 1 and this 2. So the total area, you can even call this AT if you want. A total is area 1 plus area 2. They're both rectangles, so it's length times width. Area 1 is 13 by 47. 13 by 47. Area 2 is going to be 25 by 27. Did I say 47 here? I meant 47. Did I say 47? 13 by 47. And this is 25 by 27 or 27 by 25. Multiply, multiply, add them together, get the total area. Another shape here. Another rectangular base shape, I guess you could put it that way. When you go around, you know all the lengths. This is 4, that's 4, and that's 4. No, you don't know all the lengths, but that's 12. If that's 12, and we can assume these are the same length there, we probably should have told you that they are. I don't know if you could, if we know that. Yeah, probably, you're probably missing like something that it should look like this, that this is the same length as this. And then you would say 12 subtract 4 is 8, and then divide by 2 to get 4 and 4 here. So these pieces are 4, that's 2, so that's 2. So now you just go around to get the perimeter. To get the area, I think the best way is to go the way I did down here. You could probably chop it off this way too, chop these guys off like this. The other thing you do is this might be easier, is get this whole shape here, this whole rectangle here, and then chop off the missing piece here. So if you do that, you're 5 by 12 for the big piece, and then the chopped off piece, the hollow part, is 2 by 4. So that's pretty quick actually. And you get 52 centimeters squared. If you don't see that, what you just do is break this into pieces, 5 by 4. Okay, 5 by 4. This then, if this is 4 and that's 4, then this is 4. So 4 by 4 here. Sorry, that's 3. If that's 2 length, I'm making a mess of this, but if that's 2, then this is 3. That's 4, so 3 by 4 in the middle, and then another 5 by 4 in the end. Okay, so those are all rectangles. You add them together, and my answer got chopped out, but it's 52. You get circles involved too. So when you have a circle, you got to have two major equations here. One is for the perimeter of the circle, or the circumference of the circle. So when we get the circumference, the perimeter of this entire shape, that's 20 and that's 20, and you want to figure out what that is, and you want to figure out what that is. Well, together you can probably determine that if they're both 15, a radius of 15, and remember that radius is from the middle out, not all the way across, that's diameter. If that's 15 and that's 15, then you got a circle that like you combine these two pieces, that perimeter, or that circumference and that circumference are together a whole circle. Okay, so when you get the perimeter of the whole shape, you use the circle, the area of, the circumference of a circle for formula pi d. So pi times 30. Remember that d is double radius. Okay, so you can either put that as pi d, or you can put pi 2r. Okay, 2 times r. And then the other one would be, so the rest of the perimeter is just these two pieces that are 20 each. So you go pi d, and then plus 20 plus 20. You can use whatever you want for pi. No, you can't. You can use 3.14 for pi, or you can use your calculator pi button. I think I used 3.14. I'm not sure, but I think I did. It doesn't really matter. And then you get 94.2 plus 40 plus 40. plus 20, which is 40. Now, please just give me one decimal place after a number after the decimal. Sometimes I get kids who tell me that the answer is like 0.336714, like whatever the calculator gives them. It probably isn't. Like you think about that. If we're measuring something, can we really get to the 1/1,000,000th of a centimeter? Can we measure that carefully? Probably not, right? So the best thing to do is just chop it off at 1 decimal, round properly, and you get 134.2 for perimeter. Area of this guy here, you're gonna have this, and you're gonna. So I broke it in two pieces: the area of the circle and the area of the rectangle. That says rec. Area of rectangle is length times width. 20 times. Oh, this is a little tricky, right? If that's 15, if the radius is 15, then this entire length is double the radius or the diameter. So 20 times 30, right? 15 plus 15 is 30. And that's for the rectangle. The area of the circle is pi r squared. Pi r squared. Calculator. Answer. Centimeter squared. Okay. So that's old stuff just put together. I think you can all do that. And you want to go back and maybe try some of those questions there. I'll give you a break. You can hit pause, but I'm going to keep going after this. So I'll just count to 3. 1, 2, 3. We're up to something new. Maximizing area. This is kind of cool. So if I have 16 pieces of fence and I'm making a garden in the backyard, what's the biggest garden you could make? Okay, so the fencing, we're assuming that we're making a rectangle. The fencing cannot be bent. Okay, you can't make a fence like that. So you try to make the biggest garden possible. You got 16 pieces of fence. Oops. And what you want to do is make a rectangle that is as big as possible. So you want the biggest area. So area is length times width. Okay, so the area is length times width, and the fence length is going to be in a rectangle. We're going to call this one piece A, the other piece B, the other piece A, the other piece B. We call it L and W too, length and width. Okay. So if you have length, width, like that, let me just write that out. That whole thing adds up to 16. Okay. So that means length plus width is going to be 8. So length plus 8, width is going to be 8, right? Because you have half of 16 is 8, and one length and one width is going to be 8. Now to find the area, what we do is figure out the different ways we can make a garden. The first one is going to be a nice skinny guy like this. That is 7 by 1. So we have a length of 1 and a width of 7. Now you probably realize that's the same as going like this. You can call that the length. You can call this the width. It doesn't really matter which one's the length or the width. When it comes to area, you're going to multiply them anyway. So it's 1 times 7, and you get 7 meters squared. Okay. You can make it 2 by 6. Again, remember length and width have to add up to 8. If it is 2 by 6, then you get 12 meters squared. Okay, so we're getting bigger. It's bigger than 7. Okay, so 2 by 6 is something like this. 3 by 5 is getting close to a square. Okay, so 3 by 5, and that would be a 15 meter squared garden. 4 by 4 is a square. So you got a square. They're all the same length. 4 by 4, and you get 16 meters squared. So I'm still getting bigger. And that's the biggest one you're going to get, right? Because if you go 5 by 3, you're back to where you were with 3 by 4. And you realize that in all cases, if you did this, the largest area is going to be a square. So given a fixed perimeter, the biggest area you can get is a square. Okay? And vice versa, you could also take it this way. If you're given an area, the most efficient way to build something. So if you have blocks, right? If I had 16 squares and you want to have the smallest perimeter, what you're going to want to do is build a square also. If you build something really long, okay, 16 in a row, let's just go to extremes. If you go 16 in a row like this, you're going to have 16, perimeter of 16 on top, perimeter on 16 on the bottom. That's 32, 33, 34. But a 4 by 4 blocks will have, that's 3 by 3, but if you had 4 by 4, you would have 4, 4, 4, 4. You have a perimeter of 16. Okay, so the most efficient shape for area, if it's a rectangle, is a square. Okay, so that's one thing that's new. The next thing that might be a little more difficult to figure out, you might have figured that out, is what happens if I'm building against the house. Okay, so you got a big house, or you have a house here, and now you have the same situation where you're building against the house. Okay, so the garden is going against the house. you're not going to put fence against the house. You don't have to. You get the wall, right? So here you're going to put fence, here you're going to put fence, here you're going to put fence. We're still making a rectangle, no weird triangles or anything like that, or circles. And the question is, what's the most efficient in this case? So in this, what's going to get you the biggest area in this case? Okay. So here we're going to call that 2A. And we're going to call this A. We're going to call this A. And we're going to call this B. You could also call it W and L if you felt like it, right? But we're going to just call it A and B here. And again, my area is going to be A times B, but my perimeter is going to be a little different. Okay. My perimeter is going to be that A plus A, or 2A. This plus this and this, so A plus B, or 2A plus B, is going to be 16. So this takes a little more care when I make the table. What I have here is if A is 1, then I have 1, 1, and that leaves me 14. So 1, 1, and 14 gets me an area of 14 meters squared. If I switch to 2, I got 2, 2, that's 4, and then I have 12 left, right? So that's 2, 2, and 12. And that's going to be a little squarer, okay? So that's 24. And then you might say to yourself, no, the answer is going to be a square. The answer is going to be a square, but it's not. It's not a square. Well, in this case, we can't even make a square, but in general, it's not a square, okay? So what happens next, you go 3 by 10, and that's a little squarer still, okay? If that was 2 by, if that's 2 by 12, actually, it would be more like this, a little wider like that, a little shorter like that. And that's going to be 30, and the next one's 4 by 8, and if you go 4 by 8, you get 32, and then if you go any bigger, you get smaller again. Okay, and if you go wait a second, what about if it was a square? Could I get a square? Okay, so let's change the question. Let's say I had 20. Okay, so if I had 20 pieces of rectangle left, or of fence, then I could make a 5 by 10 by 5, and that's going to get me 50. If I was going to make a square, oh, I messed this up again. I need something that's divisible by 3 and divisible by 4. So that would be 12. How about 12? Okay, let's start with 12. So if I had 12 pieces of fencing, okay, and I could go here and I could make a square here that's going to be 4 and 4 and 4. That's 12, okay, against the wall. And that's going to give me a perimeter of 16. But if I'm against the wall and I go 3 by 6 by 3, I get an area of 18, okay? Because you want to maximize the amount of free fencing, right? But then you don't want to make it too big, right? You don't want to make it too much free fencing, because too much free fencing is going to get you too skinny and your area is going to be too small. Okay, so you want to mess around with this, and if you look at this, 3 by 6 by 3, that's the maximum. Okay, 4 by 8 by 4, that's the maximum, and what you realize is the maximum area is going to be a situation where you have, in this case here, we call this, if we call this S and S, side length, that the free side is twice as long as the non-free sides. Okay. So any sort of three-sided against the house type shape, when you do a question like this guy and this guy are going to be half as big as this guy. Okay, so if you want to know how big each side's going to be, what you do is you go, this is S and 2S and another S, that's 4S to find the 4S is the perimeter. So to get each side length, what you do is you take the perimeter and divide by 4. So in this case, let's go back to where I started. If I had 16 pieces of fence, or 60 meters of fence, I divide by 4, and I get 4, and S is now 4, S is 4, so this is 4, this is 4, and this is 8. Okay, going back over to this guy here where I had 12 meters of fencing, you go 12 divided by 4, and that's 3, so this is 3, this is 3, and this is 6. Okay, that's the most efficient fencing you can get. Oh, I almost dropped my whole thing. Same sort of thing kind of happens when we look at maximize the volume of a three-dimensional shape. Sorry, I was going to say three-sided shape, three-dimensional shape. And what happens when you maximize the volume of a three-dimensional shape? So that's given an area. So given a certain amount of surface area. So you can picture this: you have a bunch of cardboard and you're making a box, and you say, what's the best box to give me the most volume? Well, you look at this guy here and you go, that's probably going to be too skinny, right? And then you look at this one here and you go, I don't know, that's a little better, okay? And then you go, how about this here? What about this one, right? Is this going to be the most efficient shape here? And I just sort of, this is like the Rogers Center. Which one is going to give you the biggest volume? What's going to have the most space inside, right? This is more like the CN Tower. This is more like the Rogers Center. This is like a regular skyscraper. So this is some bank downtown Toronto. this is going to be like your CN Tower, and this is going to be your Rogers Center, or your Sky Dome, for old people like me, which apparently they're going to tear down soon. Who knew? So here, what's the most, what has the most volume in it? It's going to be your Rogers Center. It's going to be your cube, okay? And the truth is, the more cube-like, the more efficient, okay? So what that means really is this: if you have a certain amount of paper or cardboard, and you want to make something that's going to house the most stuff in it, okay? So you're going to make something that is more cube-like, okay? And that will maximize the volume. So given a surface area, you increase the volume, you're more efficient if you're more cube-like, okay? So picture, you know what you can really picture? You ever see those things people have in their front yards? They get those giant things of soil dropped off, okay? And it's like a big bag of soil. And it's a big cube of soil, okay? That's the most efficient way to drop off soil, okay? And to house soil is in a cube-shaped bag, okay? If it was too, you're not going to get a CN Tower of soil, okay? That's very inefficient. First of all, it's hard to carry, but even if you put that on its side, it's not going to be efficient, right? So the most cube-shaped is given us a certain surface area, is going to be the biggest volume, okay? Given a volume. So if you want to say to yourself, how can I be the most efficient? What's the most efficient way to get yourself to carry a volume? You want to decrease the surface area. Okay. So what I'm saying by that is, if you're trying to wrap one of these gifts, okay. So let's say these were the same volume now. So we're going back and we're saying this is a liter, and this is a liter, and this is a liter, and you're going to wrap this up, okay? So a liter, I know a liter we usually use for liquid, but you could also use it as a measurement, an equivalent measurement, I guess, of space, right? So you could picture a cubic centimeter, okay? So 1 cubic centimeter is equal to a milliliter. So I'm kind of messing this up, the analogy, but what I'm trying to say is, if you were to wrap this up and wrap this up and wrap this up as gifts, okay? So right now you might be wrapping some gifts, and you say to yourself, what's going to take, they're all the same volume, so I got a volume and a volume and a volume, they're the same size of something. So I can't think of an example of that, but if this was just something that was, 1,000 cubic centimeters or something like that, and this was 1,000 cubic centimeters, this is 1,000 cubic centimeters, and you're asking yourself, what would use the least amount of wrapping paper? Well, this would, okay? So if you're gonna wrap like a shirt and you don't care what it looks like, and you want to use the least amount of wrapping paper, you scrunch it up in a ball and wrap it up like that. Okay, that's a horrible thing to do. Don't do that. Okay, but the more cubic it is, the more efficient it is. It decreases surface area given the volume. Okay, so here's some examples here. These guys here all have the same surface area. They're 24 centimeters squared, and you could figure that out. That the surface area calculations is a bit long, so you could go and look it up and figure out how to do that. We might look at that in a second here, but you would basically, for surface area, you have to find the area of this side, the area of that side, and the area of that side, and then double it, okay? Because you have 2 fronts, 2 sides, and two tops, like a top and a bottom, right? So that's the surface area, but the surface area here is 24. Okay, so if you figure this out, it would be 24. If you figure out the surface area would be 24, and you figure the surface area here would be 24. But if you figure out the volumes, which is length times width times height, okay, 1 times 1 times 5.5, 5.5 cubic centimeters, 2 times 2 times 2, 8 cubic centimeters, 3 times 3 times 0.5, 4.5 cubic centimeters. The key is this: this guy here is more cube-like, therefore it has the biggest volume. Okay? So that will be the most efficient way to get a volume. Next up, cylinders. Same sort of thing with cylinders. Okay, a cylinder that is more cube-like. I know that's not really right, but picture if you can have something that's more like a cube in the cylinder, the most efficient, again, is going to be the one that is the most cube-like. And in this case, what you really want to do is you want the height to be the same as the diameter. So if the diameter, which is 2 times the radius, okay, you want the height to be 2 times the radius, or you want the height to be the diameter. So let's just go over that again. Here is the base of a cylinder. If this is the diameter here, okay, right across, then if you're going to go ahead and, this is not the best drawing, but if you're going to have a height that is the same, that guy there is going to be the most efficient. So given a surface area, it will have the biggest volume. Or you can think of it this way, given a volume, it'll have the smallest surface area. So this is a question if you were trying to minimize the amount of plastic for plastic bottles, okay? So you have cylinder bottles and you're asking yourself, which is the best shape, the most efficient shape? And you've probably done this at home where you get a cup of tall glass like this, and then you get a short glass that's more square-like, right? Where the diameter and the height are closer, okay, more cube-like, where it's a little more, the height and the base are more equal, okay, more similar. What you're going to realize is the volume on these guys is a lot better than the volumes of these tall, skinny guys, right? And this one here, where you have a cylinder where this is the same, this is D, and the height is the same as the width here, or the diameter is equal, the height is equal to the diameter of the top, that's going to be the most efficient shape. Now, why don't they make plastic bottles like that? Like, why don't we walk around with bottles like this? It'll save plastic. The problem is, this is, A, it looks better, okay? And B, maybe it tricks people. Maybe you go, hey, I got more, maybe it tricks your eye, right? And you go, oh, maybe I'll have that, right? I'll have that guy there because he looks like it's got more in it. But probably the real reason is, think about the size of your hand, right? You want to make this circumference, I don't know exactly how they do it, but it's got to be handheld, right? So if you minimize here with the circumference of this guy, because it limits your hand, right? Limit by the size of your hand. You don't want something that doesn't fit your hand, too big, right? Then what here, if the circumference is going to be the size of your hand, but you can make it taller, well, you probably will do that because you can sell more stuff, right? And then you go, well, why don't we just make it bigger? It'd be better and better. Well, I don't know. Think of drink holders. Think of all that, right? Nobody says, hey, let's buy a cube of milk, right? Or let's buy a cube of water, right? The shape of it goes like this, right? The shape is more more streamlined, I guess, skinnier. Okay, but think of the bags of milks. First of all, think of a bag of milk. What a bizarre concept. Sometimes I go off on this, but think about that. You take milk in a container, and then you take the container, which is a bag, and then you put it in another container. Very bizarre. We're some of the only people on Earth that have bags of milk. Okay, the rest of the world just use containers. They don't use jars, but that'll be interesting. Okay, jars of milk. Anyway, back to this. More cube-like. Okay, so more cube-like is more efficient when it comes to things that have to have 90 degrees. Okay, if you have things like this, where you're talking about cylinders, the most efficient is where the diameter and the height are equivalent. Okay, so the diameter and the height are equivalent. And then you can ask yourself this: what about if I can choose between them? Which is the most efficient? And this one, I don't know really if you'd be able to figure this out, if I would be able to figure it out, anyone would be able to figure this out. But if you look at this right here, if you have 1,000 cubic centimeters, okay, which is the equivalent to a liter, it's the same as 1 liter, and you're going to figure out which of these is the most efficient, which uses the least amount of wrapping paper or plastic or whatever the outside is going to be. I don't know if you get this or not, but the most efficient is actually the sphere. So the most efficient is the sphere, and second place is the cube, and third is the cylinder. Okay, why is that? I don't know. Okay, maybe you can picture that in your head, right? Why this is the most efficient? I guess there's less waste here, right? You're just, you're wrapping it up in a ball. You got a certain amount of volume. The most efficient here is going to be more ball shaped. This one here, is that more spherical than that? I don't know. I guess it is. Okay, so this guy's more efficient than this guy. Okay, but this is number one. Other way around is if you have a certain amount of wrapping paper or a certain amount of plastic and you want to maximize the volume, okay, that's not the question here, but it would be the same thing. This guy would be the most efficient, this would be second, this would be third. Okay? Who knew? Okay, so that's it. I think that's it. And then there are just questions here. Okay, so there are some questions here about finding 3D surface areas and 3D volumes. This stuff here, you just use your equations Okay, so go over this. Questions like this are going to be a little confusing when you look at the cone. Know that this is your S. So let me just put this down a bit here. This is your S. This is your H. So if you have to figure one of them out, you have to use Pythagorean theorem. So in this case here, I think I had to find H out for the volume. I did, right? So to find H, I used Pythagorean theorem to figure out that H was, where did I do that? H, down here. H is 6.7. Okay, so Pythagorean theorem is makes this 6.7. And then from there, you just sub those into the equation. So a cone has a surface area of this, sub it in. Has a volume of this, sub it in. Okay, and then get your answers. Remember that surface area is area, so it's squared. Volume is going to have to be cubed. This one here, same thing. You got a crazy equation here. Okay, so surface area of a triangular-based prism. What you're doing is you get the area of everything. Okay, so you can go ahead and get the area of this triangle and the area of this triangle, and then know that there's a rectangle on the bottom, a rectangle on the back, and a rectangle on the top. And you can go ahead and do that to get the surface area, or you can go ahead. You can just use this equation: BL plus AH plus BH plus CH. You just gotta be really careful to know what's what. But as long as you don't mess up, you should be okay. This is A here, so that length is A. This is what they call L. So when you look at your equation formula, that's what you see is that A and L are these two guys, and that C. C is this guy right here. Okay, so C is here. So if you don't have that, again, you might have to use Pythagorean theorem. Here we have it though. Okay, so you have those there, and then the other one that you don't know is this guy right here, which is 9. Okay, and this one here, 9 is your H. So they call that H. Am I missing something here? No, I got this. B. Oh yeah, so hold on. So this is B here. Did I call that L? It's the same thing. Okay, so in this case, no, it's not the same thing. Let me see what's going on here. So here I got the base times the length. So I go 6 times 6, and that gets me this triangle here, okay, and I double it. And then I have A times H. So A times H will give me the back side. So I just want to make sure I'm doing this right. A times H gives me the back rectangle. That's 6 times 9. Okay, 6, and that's 9. Then you want to get this bottom rectangle here, okay, and that's 6 by 9. So this is, again, B, and that's H. And the last guy here is going to be 8.5 by 9 here. So they call that C. You got to check that equation out for me. But this could also be A times B. Okay, A times B instead of B times L. Okay, but either way, you get the surface area of that triangular-based prism. To get the area, that's the area there. Yeah. So that's with the formula. Sorry, that's for the formula. What I did below was I said, let's break it up into pieces. The area of the triangle there, the rectangle there, the rectangle there, the rectangle. So you can do it that way too if you don't like the equation. Okay. So what you're getting is the triangle, and you double it because there's a front and a back triangle. Okay. Then you get the area of the different rectangles. This is 9 by 8.5. So 9 by 8.5 is the front. I did the top first. 6 by 9 is going to be the let me figure out what that is. 6 by 9 is the back. Okay. And the bottom is also 6 by 9. So in this case, they're both 6 by 9. To get the volume, it's just 1/2 BLH. Okay, so 1/2 BLH. So it's 1/2. So basically what you're doing is you're figuring out how big the rectangle is. Okay, so the triangle is. So it's 1/2 BLH will give you the area of the triangle, right? Because the area of a triangle is this. And then what you do is you multiply by the height, essentially. So if you can picture this upside down almost with a triangle on the bottom, it's almost like a cylinder where you have, like, if I could do that, no, I can't do that, but if I drew that like that, going up, you get the area of the triangle, 1/2 B times H, and then, or L, sorry, they call it L, and then you're going to multiply by the height of the triangle, of the prism. Okay, so that's that. Cylinder, oh, this is a good question. A cylinder just fits inside the box. How big is the cylinder? What's the volume of the cylinder? So if you had a cylinder that just fit in here, okay, like this, you might say, oh, I can't do that. Sure you can, okay? So it's got a height of 6. Okay, the cylinder has a height of 6, and then you got to find out the radius. But if this so if you look at this, so I'm just looking from the top, okay, and this guy was 4 by 4 by 4, okay, because it's a square. This guy here is going to be length of 4, okay, so it's the same length as this. So that's your diameter, so your radius is 2, and then you go from there. Okay, so the radius will be half the length of the top square. Kind of cool. Okay, and then you just sub it into this, pi r squared h. So here are all your formulas. So the formulas are all here. Anything you need will be here. So again, so this guy a little confusing here for me. So the key to this is with the triangle is your B and your A and your C may be different. They may be the same. So the problem not the problem, but what happened in this question here was it's a right angle triangle. So in this case, your right angle triangle, your B and your B and your C will be the same. Okay, so it's a little confusing. Okay, but maybe if you look over this, you could take a look at and find out. But again, what you can do is if you don't like this, at all, then go ahead and get the area of this. Okay, figure out what that is. Get the area of this, get the area of that, and get the area of that. Okay, so there's 3 rectangles and there's 1 triangle. Okay, and then you'll have to double the area of the triangle because there's a triangle on the bottom. Okay, so that might be an easier way to do it than trying to mess around with this equation. So what you're going to do is you're just going to answer these questions. Okay, so your pink piece of paper looks like this. You're going to go ahead and answer these questions to the best of your ability. Okay, so you're going to have to use Pythagorean theorem for the first one. Here you have a weird shape. You want to build a floor. What's the minimum perimeter? So this is like your garden question. Okay, so you can mess around with that one. This one here is a composite figure. So you got a composite figure. You can play around with that. Here you're looking at surface area. Find out the surface area of this prism. What's the surface area of this question here? And then you're going to keep going with spheres and that sort of thing here. And this question at the bottom is really neat. The volume, 25 balls, each with a diameter of 9 centimeters. So each of these is 9 across. So if I take one of the balls here, they have a diameter of 9. But know that each ball is a sphere, right? So I have a sphere with a diameter of 9, which means they have a radius of 4.5. That might be important. They have a diameter of 9. That might be important. Okay, I'm not going to give too much away here. But think about this. You have 25 balls, so 5 by 5. Okay, so if each ball, if I had 2 balls here in diameter of 9 like that, okay, then if this was a little box that was this big, I would have 9 by 9. That'd be 18 by length here. Okay, and if it was just 2 by 1, then this guy here would be 8. But if it was 2 by 2, this would also be 18. Okay, so take that and think about this. If each one of these has diameter of 9, and then they're 9 tall, what happens? And if you can do this, you're really advanced. Okay, so just get that pink sheet done. Hopefully this video wasn't too confusing. That triangle thing was a bit strange. And good luck. Have a great break. See you when you get back. Take care.